few slides. Okay, as we were talking about the technicality, however, in this lecture, of course, we're talking about the primary attention of refrigerant is mainly focused on the fluids that can be used as refrigerants in our vapor compression refrigeration systems. So we have a common understanding of what we're referring by refrigerants. How do you classify refrigerants? What's the classification method?
Primary and secondary?
Yes. So ultimately, we can classify them as primary and secondary refrigerants. Okay? And we'll look at in a minute the definitions of what a primary refrigerant is, what a secondary refrigerant is. So the primary refrigerant is the refrigerant that we have inside here, which is constantly and continuously changing its phase from gas to liquid, gas to liquid, constantly changing its phase. So the primary refrigerant is always changing its phase from gas to liquid, back liquid to gas, and then gas to liquid. Okay, so those are the primary refrigerants that we are referring by primary refrigerants. And the secondary refrigerant, I'm sure by now you've guessed what they are the medium that we use to reject the heat into the atmosphere. Secondary refrigerants, so here, for instance, when we look at the condenser, we've looked at how to classify condensers, and we say we can classify condensers based on either water-cooled or air-cooled condensers on the secondary circuit. So for instance, here we can see two ways, which is, so the yellow animation is assuming it's water that we're using. And then of course we've also got fan here, which is blowing air to there. So the secondary refrigerants, we are referring to the secondary medium that we're using to extract the heat from. Okay, so we can use water as a secondary refrigerant if, of course, the operating temperature is above 0 degrees C. Okay, so provided that the environment that you're in is above 0 degrees C on the secondary circuit, we can use water as pure water as a refrigerant. But the only time that we may have difficulty is in areas where it's colder. Okay, so therefore, of course, water will start to freeze, and the solution to that, of course, we use antifreeze solutions, so the brine solutions here. Okay, so the question to can we use water as a refrigerant? Of course, we're using water as a refrigerant on the secondary circuit, but we can also use antifreeze brine solutions to minimize the freezing aspect. So now we know the refrigerants can broadly be classified as primary refrigerants. The primary refrigerants are constantly changing its phase, and then also the secondary refrigerants on secondary circuit are the medium that we're using to extract the heat. It could be water, or it could be air. So those are the secondary refrigerants. Okay, so if one was to ask you what's the difference between primary and secondary refrigerants, the primary refrigerants are constantly changing their phase. They're constantly boiling and condensing. Okay, so inside the circuit, so we've looked at here, the primary refrigerants are constantly changing its phase from liquid to gas, and gas to liquid, liquid to gas. Okay. Whereas the secondary refrigerants, they do not change their phase. They are constantly or always liquid. They don't necessarily have to change their phase. So that's primarily the difference between primary refrigerants and secondary refrigerants. Primary refrigerants are always changing their phase, but the secondary refrigerants don't change their phase or state. Okay, so now that we know the definition of a refrigerant, and we also know how to classify a refrigerant, what are the selection criteria for selecting the best refrigerant? Primarily, 4 selection criteria that you need to consider in order to select the best refrigerant. The thermodynamic and thermophysical property. We will look at one by one what we are actually referring by thermodynamic and thermophysical property. that is an important aspect for you to decide what kind of refrigerant that you may want to use in a system. Environmentally friendly, again, one of the primary and dominant discussion that we are having everywhere is how we can develop, how we can have an alternative low GWP refrigerant, how it needs to be, non chlorine and fluorine and bromine containing chemicals or substances. Safety consideration. Again, we'll look at what we are referring by safety consideration. You don't want to specify a chemically hazard refrigerant. Again, we'll look at one by one what we're actually referring by safety considerations. And economics, of course, the cost is the first aspect that you guys have talked about. Is it well proven? Has it been used before? Is it low cost? And availability, again, BJ, you've talked about. Would it be available for the medium to long term? Okay, so those are the 4 primary selection criteria that you can consider in order to reach in selecting the best environmentally friendly refrigerant. Okay. When we talk about, so we've talked about the thermodynamic and thermophysical properties, and let's look at what we meant by thermodynamic and thermophysical properties and how we should consider thermodynamic and thermophysical properties. So now, so far, when we've looked at the vapor compression system, we've looked at the importance of the relationship between pressure and temperature. And we've looked at if you increase pressure, you also increase the temperature. If you reduce the pressure, you also reduce the temperature. So the boiling point and the freezing point of a refrigerant in terms of the temperature and in terms of the pressure is one of the criteria that we need to consider. The discharge pressure and the pressure ratios. So again, we've looked at how a system, depending on the pressure ratio, depending on the condensing and evaporating pressures that you operate, a system could perform well in terms of the COP of the system, or it can struggle to perform therefore very low COP, because the higher the pressure ratio, again, those of you who did the experiment, you may have started to plot this and look at the relationship between how the condensing pressure and the COP and what the relationship is. The higher the pressure ratio, the lower the COP, the higher the power consumption of the compressor. Okay, so temperature, the pressure relationship of any refrigerant is another important aspect. The latent heat of vaporization. Again, we've looked at how we can calculate based on the mass flow rate of the refrigerant and the heat of vaporization, the difference between the inlet and outlet of the evaporator, and also if you know the freezing and boiling point of a refrigerant, indirectly it also tells you the amount of heat that you may need or you may require to boil and to freeze that refrigerant. And ultimately, of course, it's that energy that we're interested in. If we can get away with a very, very small amount of energy input into the refrigerant, then it's preferably. We've looked at the isentropic index, how it's important. Again, the type of refrigerant that we use, but ultimately the overall losses in the system are also interlinked between the two. Specific heat, again, importance of the properties of the refrigerant in terms of the specific heat of the refrigerant that we're using. We've talked about the boiling point, we've talked about the freezing point, and again, the density that would also affect so when you have a very, very dense refrigerant as opposed to slightly less dense refrigerants, because that would also affect the pressure drop in the circuit. Again, when we looked at the expansion valve, we looked at how the pressure drop and the viscosity are other important parameters that we need to consider, because they also relate to the pressure drop in the system, and therefore, of course, the temperature drop in terms of the refrigerants. So all these parameters are what we call thermodynamic and thermophysical properties of the refrigerant, and we need to consider all these aspects when we select any refrigerant. Okay, so that's what we were referring by the first selection criteria, looking at the thermodynamic and thermophysical aspect. The second selection criteria that we looked at is the environmentally friendly, or the impact to the environment. So the environmental impact of the refrigerants, but of course the refrigeration in total, or the systems that we use in total. Now, it wasn't until late around 1980s or 1987 to be specific, that researchers have found out that CFC is becoming a major distraction to our lower atmosphere, or our ozone. Okay, the fact that when we release, or if there's a leakage from the refrigerants that we use, which contains the CFC type of refrigerants, and if they react with the sun's UV or the ultraviolet rays, they easily break down the compound. So they release, as a byproduct, they release chlorine, which chlorine is responsible for facilitating the depletion of the ozone, or the thinning of the ozone. So it was around 1987 that they started to talk about the CFCs and the impact of the CFCs, and how the byproduct of the CFCs, which the chlorine molecules reacts, and the impact of that is the depletion of the ozone layer. So because we're talking about some of the chemicals are thinning or depleting that layer, which is the ozone layer, or the lower part of the stratosphere level of our universe. Ultimately, the function, if you look at in a layman term, a ozone layer is used as a blanket to the to Earth, or to us. So it protects us from, as you said, unwanted UV rays coming in from the sun. Okay, and imagine if we start interact and start impacting this layer, if it gets thinner and thinner, it means we will be exposed to quite a lot of unwanted radiations, or solar radiations. In a minute, we'll look at few of the impact of the if you're exposed to solar radiation. So in general, we are talking about, when we look at the impact of the refrigerants and some of the chemicals that we're using, we're saying they're responsible for the depletion of the ozone layer in the stratosphere, or in our ozone layer. And we're also saying they're responsible for the global warming through the direct impact, which are the leakage, and the indirect impact, which are the fact that we need electricity to operate the systems. That's what we're basically saying the benefits of our ozone layer, filters dangerous ultraviolet rays coming from the sun. So it's important that we deal with or minimize the impact of the depletion of the ozone layer. Otherwise, we will cease to exist. And this is a just another example showing what the process of once there's a leakage or once you start to release CFCs and what happens and how it reacts to the sun and how the sun breaks down the CFCs. And ozone is O3. The formula for ozone is O3, and how these chemicals can easily break down ozone into a smaller molecule of it, which is O2. And of course, as you can see, that's how it breaks it down. That's how it thins it down. It can easily react and therefore thin it down to oxygen. And ultimately, we're talking about CFCs, HCFCs, which have ozone depleting substances. We will look at in a minute what we are referring by ozone depleting potential or ozone depleting substances. Ozone depleting substance, primarily we're just referring to refrigerants which contain chlorine, fluorine, and bromine. Okay, and those chemicals tend to impact and easily react with ozone and facilitate the thinning or depletion of the layer. So we talked about what happens if you thin it. Ultimately, there is huge implications. Let's just look at just only two implications. How high exposure to UV rays can easily cause skin cancer of the ozone depletion. When we've looked at the exposure to high UV rays can cause skin cancer, the impact of the refrigeration generally, and what the implication to that to our global warming and how we contribute into our global warming is. And primarily, approximately 1/4 of the effect is through direct impact, directly due to the leakage of the refrigerants, and 3/4 is generated through the use of electricity. So the indirect impact is a direct impact. Of course, direct impact is the leakage of refrigerants, and the fact that we've seen in the previous slide how they react with the sun's UVs and how they can easily break down or facilitate the depletion of the ozone. So that's through the direct impact through the leakage of refrigerants. And that the indirect is the fact that we need to supply electricity to the systems to operate. And in order to generate this electricity, we need, unless we're using renewable energy to generate the electricity, the chances are we will be using fossil fuels. So therefore, we are also emitting carbon into the atmosphere in order to generate the electricity for supplying the system's electricity requirement. Okay, so that's what we're referring by the direct and indirect impact of refrigerants and also refrigeration systems. Okay, so I think in the past few slides I've used word ODP or ODS, ozone depletion potential, or ozone depletion substances. I've also used words like GWP, global warming potential. So let's look at some of the definitions, and so when anyone is using them, so you have a better understanding. So by ozone depletion potential, or by ODP, we are actually referring to the ability of a chemical or a substance to destroy the stratospheric ozone. And we've looked at earlier in the 1987 how researchers started to discover the CFCs are having an impact to the stratospheric ozone. So our benchmark is the CFCs. So we compare all refrigerants to the CFCs, which has an ODP of 1. So when we talk about ODP, we are comparing them to CFCs. We look at in GWP, and again, our benchmark, our index is the carbon dioxide. So in the ODP, when we talk about ODP, primarily, we are talking about whether the substance or the chemical that we're using contains chlorine, fluorine or bromine molecules. That's what it means. And we're comparing it to the CFC being the benchmark. Okay? So if someone is talking how the refrigerant is a 0 ODP, they're purely saying that the refrigerant does not contain chlorine, fluorine, or bromine, or any halogenated compounds. ODP or ODS is the ability of any chemical or any refrigerant or any substance to destroy the stratospheric ozone. The ODP depends mainly on the presence of chlorine, fluorine, or bromine, as I said earlier. So that's one index that we use to categorize refrigerants and how the substance or the chemical may contain some harmful chemicals that can easily destroy our stratospheric ozone. Okay, so this is for destroying our ozone layer primarily. Okay, and there is another index that we use, which is called the global warming potential. Okay, so we've looked at ODP and how ODP is referring to the presence of the chlorine, fluorine, and bromine. And we can compare ODP to our benchmark, which are the CFCs. And the GWP, similarly, we use the CO2 as an index. Okay, and the definition of a GWP is the ability of a greenhouse gas or a substance to trap heat. And I briefly talked about this earlier. When we compare the different types of refrigerants, some of them are very, very highly in trapping heat. Okay, so ultimately the GWP or global warming potential deals with the ability of the substance to trap heat in the atmosphere. And everything is compared to relative to carbon dioxide. Okay, because when we talk about global warming, we talk in terms of the carbon emissions, the carbon dioxide emissions. So our benchmark or our index is the CO2. So on the ODP, our benchmark is compared to CFCs, the value of CFCs being 1. And in the GWP, it's compared to CO2. Okay? And the index of the CO2 having the index value of 1. Again, so we'll look at some examples. So if we say a GWP of 100 of 10, so that means that the substance or the chemical will trap 10 times as much heat as the same mass of CO2 over 100 years. And when we look at GWP, they are measured over the impact over 100 years. Okay, and the GWP is calculated, and it changes with time, but over 100 the impact and the existence of that refrigerant over 100 years. In ODP, we're mainly concentrated or interested in whether the substance has chemicals like chlorine, fluorine, and bromine, and our benchmark are the CFCs, 1. And in the GWP, we're interested on the ability of the substance or the chemical to trap heat, and everything is compared to CO2. CO2 being 1. And we'll look at some of the examples. For instance, let's take methane. 1 kilogram of methane causes 25 times more warming over a 100-year period compared to 1 kilogram of CO2. So as I said, everything is compared to CO2. Your CO2 is 1, a value of 1. So in general, we can say methane has a GWP of 25. Okay, so preferably, again, coming back to the question that we've introduced at the beginning, you would want a refrigerant which have as low GWP value as possible. Okay, of course, to minimize and reduce the global warming. You may have refrigerants with 0 ODP. By 0 ODP, meaning the refrigerant you're using does not have chlorine, fluorine, or bromine, but they may have a very high value of GWP. A good example that we've been using for the labs is the refrigerant R134A. There's also a dilemma between the two indexes that we're using. The refrigerant might be 0 ODP, but on the other hand, it might have a very, very high GWP values. Okay, so we have to be able to balance. So there may contain ODP aspect, but the GWP is very, very low. So these are some of the GWP values for the different refrigerants that we use. So carbon dioxide being our benchmark, 1. We said methane is the ability of methane to trap heat is 25 times than carbon dioxide. The ability of, if you use HFC refrigerants, the ability of the HFC refrigerants to trap heat is 11,700 times than carbon dioxide. So as you can see, if we're using HFC, and compared to carbon dioxide, they are extremely very, very high capability in trapping heat in the atmosphere. And so I'm just giving you a few examples to understand what we meant by value of GWP. So everything is compared to carbon dioxide.